Breaking news from the edge of our solar system. 3 Atlas is no longer behaving like a simple comet. Days ago, astronomers watched as this interstellar visitor crossed within 2 astronomical units of the Sun and began brightening far beyond predictions. Its atmosphere has swollen to half the diameter of our star. Its glow has shifted to an unsettling green, and most bizarrely, it's developed a tail pointing directly toward the Sun, something that should be impossible. As it races toward Mars at breakneck speed, researchers admit they can't explain what they're seeing. The countdown to perihelion has begun, and with every passing hour, this alien wanderer looks less like a comet and more like a cosmic riddle demanding answers. Stay until the end of tonight's exploration to learn what this breaking story means for everything we thought we knew, and what happens when alien chemistry finally awakens. Part 1. It's getting bigger and brighter. The numbers don't lie, even when they defy explanation. In mid-September of 2025, astronomers monitoring 3I Atlas noticed something unsettling in their data. The brightness measurements began climbing above the predicted curves, rising from the expected magnitude of 15 or 16 to a startling 12 to 14. For those unfamiliar with the backwards logic of astronomical magnitudes, this represents a dramatic shift. Think of it this way. Magnitude numbers run in reverse. The lower the number, the brighter the object. A drop of just 2 magnitudes means the object is now producing 6 times more light than predicted. But this wasn't a gradual change. This was acceleration. The Comet Observation Database, known as COBS to those who track these celestial wanderers, began showing data points that climbed steadily above the standard upward slope expected for a warming comet. Earth's skies tracking confirmed the trend. 3 Atlas was outshining every model astronomers had constructed for its journey sunward. The critical moment came as the object moved inside approximately 2 astronomical units of the Sun in early to mid-September. For context, 1 astronomical unit is the distance from Earth to our star, roughly 93 million miles. At 2 AU, 3I Atlas was still twice as far from the Sun as we are. Yet something fundamental changed. The brightness acceleration wasn't just unexpected, it was alarming in its intensity. What could cause such a dramatic surge in luminosity? The most likely explanation involves volatile ices, frozen carbon dioxide, water, and exotic compounds locked within the nucleus since the object's formation around another star. As solar radiation intensifies, these materials don't just melt, they explosively transition from solid to gas, carrying dust and debris and expanding clouds that reflect sunlight back toward Earth. But here's what should concern us. Rapid brightening events often signal instability. Comets experiencing sudden outgassing can fragment, creating multiple objects or spectacular debris clouds. They can also exhaust their volatile reserves quickly, leading to equally rapid dimming. The fact that 3 Atlas is brightening faster than models predict suggests we're witnessing processes that astronomers don't fully understand. This isn't cause for planetary panic, however. NASA has confirmed that 3I Atlas maintains a safe distance, never approaching closer than 1.8 astronomical units to Earth, nearly twice the distance to our Sun's position. The alarm isn't about collision, it's about comprehension. We may be watching an interstellar time capsule undergo fundamental changes in real time, as it barrels toward the inner solar system. Consider the implications. This object formed in the disk of debris around another star, perhaps hundreds of light years away. It condensed from materials that never felt our Sun's warmth, never experienced the specific conditions that shaped the bodies native to our cosmic neighborhood. Yet now, for the first time in its existence, it's encountering the intense radiation environment of our inner solar system. The brightness surge could represent the awakening of chemistry that has remained dormant for millions or billions of years. Exotic ices, stable in the frigid depths of interstellar space, might now be sublimating for the first time since the object's birth. We're potentially witnessing the unveiling of chemical signatures from another star system, preserved in pristine condition across the galaxy. The timing creates additional urgency. 3 Atlas is approaching a series of critical dates that will determine what astronomers can learn from this unprecedented visitor. October 3rd marks its closest approach to Mars, a mere 30 million kilometers, close enough for spacecraft orbiting the red planet to potentially observe details invisible from Earth. By late October, specifically October 29th to 30th, the comet reaches perihelion, its closest approach to the Sun, at approximately 1.36 to 1.4 astronomical units. Here's where the story takes a troubling turn for Earth-based observers. As 3I Atlas nears its date with our star, its position in our sky moves dangerously close to the Sun's overwhelming glare. From early October through early November, the comet enters what astronomers call superior conjunction, a period when the Sun's brightness makes observation nearly impossible from Earth's surface. This means the peak activity of our interstellar visitor, the moment when solar heating reaches its maximum intensity and the comet's true nature might be revealed, will occur largely hidden from our view. We'll be forced to rely on the mechanical eyes of spacecraft positioned throughout the solar system, particularly those orbiting Mars, to witness what could be the most spectacular display of interstellar chemistry in human history. The brightening trend suggests 3I Atlas won't go quietly through perihelion. Current observations hint at an object energized by its encounter with our Sun, possibly building toward outburst events that could illuminate previously invisible details of its structure and composition. But will these revelations occur during the weeks when Earth's telescopes are blinded by solar glare? The data emerging from September's observations paints a picture of an object in transition. The measured brightness points trending above predicted curves suggest that 3C Atlas is becoming something different from what it was during its long journey through interstellar space. The question is whether this transformation represents normal comet behavior in an exotic object, or something entirely unprecedented in our experience with visitors from other star systems.
In the coming minutes, we'll explore why this object's coma extends farther than should be possible, why its tail points toward the Sun instead of away from it, and how its recent shift to an eerie green glow might signal chemical processes never before observed in an interstellar visitor.
The mysteries are multiplying as quickly as the brightness measurements are climbing. But first we need to understand what we're dealing with. Because 3 Atlas isn't just any comet, it's only the third confirmed visitor from another star system, and its behavior is already proving that each interstellar object carries its own set of rules. Part 2. Discovery and Classification. The story of 3 Atlas begins on a mountaintop in Chile, where robotic eyes scan the night sky with mechanical precision that puts human observers to shame. On July 1, 2025, the Asteroid Terrestrial Impact Last Alert System, ATLAS for short, detected a faint smudge of light moving against the background stars. Initially catalogued as just another minor body, this unremarkable observation would soon rewrite our understanding of interstellar visitors. What makes an object interstellar isn't simply its origin beyond our solar system. It's the mathematical certainty that it can never be gravitationally bound to our Sun's orbit. 3I Atlas follows what astronomers call a hyperbolic trajectory, a path so energetic that once it completes its swing around our star, it will continue outward forever, never to return. The orbital mathematics are unforgiving in their precision. This object carries too much velocity to be captured by our Sun's gravity. The 3I designation tells its own story. The I stands for interstellar, while the number 3 indicates this is only the third such object confirmed in human history. Its predecessors, 1IO Warmer in 2017 and 200 Borisov in 2019, each surprised astronomers with unique characteristics that defied easy categorization. Now, 3I Atlas continues this pattern of interstellar unpredictability. The discovery process reveals just how difficult these objects are to catch. Atlas operates from the Rio Ardo Observatory in Chile's Atacama Desert, part of a global network designed to spot potentially hazardous asteroids approaching Earth. The system captures multiple images of the same sky region over short time periods, then uses computer algorithms to identify anything that moves against the stellar background. On that July night, 3I Atlas appeared as little more than a faint streak, barely distinguishable from the thousands of asteroids, comets, and space debris that populate our inner solar system. but recovery images, earlier photographs that show the object before its official discovery, revealed that 3I Atlas had been lurking in astronomical databases for weeks before anyone recognized its significance. This delayed recognition is common with interstellar objects, which often appear asteroidal in early observations before developing the fuzzy comas and tails that mark them as comet-like bodies. The initial assessment showed a faint coma surrounding the central nucleus, immediately suggesting that 3I Atlas was more than just a rocky asteroid. Comets develop these fuzzy atmospheres when solar heating causes ices to sublimate, creating expanding shells of gas and dust. The presence of a coma so far from the Sun, 3I Atlas was still beyond 3 astronomical units, when discovered, indicated that this object contained volatile materials capable of outgassing even in the cold outer reaches of our solar system. As news of the discovery spread through the astronomical community, larger telescopes began turning toward this new interstellar visitor. The Hubble Space Telescope captured detailed images in July, while the Very Large Telescope in Chile and other ground-based observatories contributed their own observations. These follow-up studies revealed an object far more complex than its initial discovery images had suggested. Size estimates for 3I and Atlas remain frustratingly uncertain, a common problem when studying objects too distant and faint for direct measurement. Hubble's August update narrowed the possibilities to a nucleus somewhere between 0.32 and 5.6 kilometers in diameter, a range that reflects the difficulty of separating the solid nucleus from its surrounding coma. The size uncertainty matters because it affects calculations of the object's mass, density, and structural stability as it approaches the Sun's intense heating. Speed calculations paint a clearer picture of this object's extraordinary nature. Currently racing through space at approximately 30,000 mpl, roughly 58 km/s, 3I Atlas moves at velocities that dwarf anything naturally occurring in our solar system. For comparison, Earth orbits the Sun at a sedate 30 kilometers. The comet's speed will continue increasing as solar gravity accelerates it toward perihelion, potentially reaching 68 kilometers, or more than 150,000 mph. These velocities underscore the alien nature of our visitor. No object born in our solar system could naturally achieve such speeds without assistance from gravitational slingshot maneuvers around massive planets. 3I Atlas carries the kinetic signature of its interstellar origin, accumulated during millions of years of travel through the galaxy under the influence of stellar gravitational fields and galactic rotation. The rarity of confirmed interstellar visitors makes each one precious to science. Before 2017, astronomers had only theoretical models to guide their understanding of how objects might behave during interstellar journeys. 1E Oumuamua shattered many assumptions with its elongated shape and mysterious non-gravitational acceleration. 2 Boris appeared more conventionally comet-like, but revealed chemical compositions unlike anything in our solar system. Now 3 Atlas adds a third data point to this sparse collection, and early indications suggest it will prove as unique as its predecessors. The object's behavior challenges models in new ways, particularly its unexpectedly large coma and unusual brightness evolution. Each interstellar visitor seems to carry its own set of physical and chemical rules, suggesting that the galaxy harbors far more diversity and small body formation processes than we previously imagined. The classification process involves more than just confirming interstellar status. Astronomers must also determine whether 3I Atlas represents an asteroid-like body, a comet, or something entirely different. The presence of a coma strongly suggests comet-like behavior, but the specific gases and dust compositions revealed through spectroscopic analysis will ultimately determine how this object formed and evolved in its birth star system. This is not a local comet kicked inward from the Oort cloud, that distant reservoir of icy bodies that occasionally sends visitors toward the inner solar system. 3I Atlas formed around another star, condensed from materials that experience different temperatures, pressures, and chemical environments than anything native to our cosmic neighborhood. It represents a direct sample of planetary formation processes that occurred light years away, possibly billions of years ago. The trajectory calculations place 3I Atlas on a path that will provide unprecedented observation opportunities. particularly during its close approach to Mars on October 3rd. This geometry isn't accidental. The object's orbital inclination and timing align favorably for spacecraft observations, just when Earth-based telescopes will lose sight of it due to solar glare. But understanding what we're seeing requires more than just knowing where 3I Atlas came from and where it's going. The real mysteries lie in how it's behaving as it encounters our sun's radiation for the first time in its existence, and why that behavior differs so dramatically from theoretical predictions. Part 3. Trajectory and Timeline. Time is running out for 3I Atlas, and for the astronomers racing to understand it before it vanishes into solar glare, the mathematics of orbital mechanics have drawn a precise roadmap through the inner solar system, marking critical dates that will determine what humanity can learn from our third confirmed interstellar visitor. October 3rd, 2025 represents the first crucial milestone. On this date, 3I Atlas will sweep past Mars at a distance of approximately 30 million kilometers, roughly 0.19 to 0.12 astronomical units. In cosmic terms, this constitutes an extremely close encounter, placing the interstellar visitor well within the operational range of multiple spacecraft currently orbiting the red planet. The timing couldn't be more fortuitous or more frustrating, just as 3I Atlas reaches its closest approach to Mars, offering spacecraft the clearest possible view of an interstellar object in action. Earth-based telescopes begin losing their ability to track it. The cruel geometry of orbital mechanics places the comet increasingly close to the sun's position in our sky, creating observational challenges that will soon become insurmountable. By late October, specifically October 29th to 30th, 3IA Atlas reaches perihelion, its closest approach to the sun at approximately 1.36 to 1.4 astronomical units. This distance places it just inside Mars's average orbital radius, subjecting the interstellar visitor to solar radiation intensities, unlike anything it experienced during its journey through the galaxy. The timing coincides almost perfectly with the period of greatest observational difficulty from Earth. The speed evolution tells its own dramatic story. Currently traveling at tens of kilometers, 3I Atlas will reach its maximum velocity near perihelion, potentially hitting 68 kilometers, or approximately 50,000 km, 52,000 km. To put this in perspective, Earth maintains its stable orbit around the Sun at roughly 30 km. 3I Atlas will be moving more than twice as fast as our entire planet. These velocities represent more than impressive statistics. They reveal the fundamental physics governing interstellar motion. Unlike objects native to our solar system, which gain their speeds through gravitational interactions with the Sun and planets over billions of years, 3I Atlas carries kinetic energy accumulated during its journey between star systems. Every kilometer per second of velocity represents vast distances traveled through interstellar space, influenced by the gravitational fields of multiple stars and the rotation of the galaxy itself. The approach trajectory places 3I Atlas near the ecliptic plane, the relatively flat disk containing most planetary orbits. This geometry facilitates the close encounter with Mars, and will later enable a distant approach to Jupiter in 2026. The orbital alignment isn't coincidental. Objects approaching from random directions in three-dimensional space would be unlikely to pass so conveniently close to multiple planets during their brief transit through our solar system. Safety considerations never entered the equation for 3I Atlas. Despite its classification as a potentially hazardous object during initial tracking, the closest approach to Earth occurs at approximately 1.88 astronomical units, nearly twice the distance to the Sun, and well beyond any conceivable threat. NASA's confirmation of this safe distance eliminated public concern about collision, allowing astronomers to focus on the scientific opportunities rather than planetary defense considerations. The real challenge lies in observational geometry. From early October through early November, 3IA Atlas experiences what astronomers call superior conjunction, a period when its position in Earth's sky places it too close to the Sun for practical observation. Solar elongation, the angular separation between the comet and Sun as seen from Earth, drops below 30 becquerel for much of this critical period. Imagine trying to spot a firefly hovering next to a floodlight, and you begin to understand the observational predicament. Even the most sophisticated telescopes cannot separate the faint light of 3I Atlas from the overwhelming glare of our star when the two objects appear close together in the sky. This natural limitation of Earth-based astronomy means that the comet's most active period may occur largely hidden from human observation. The conjunction timing creates a fundamental irony in the 3I Atlas encounter. Just as solar heating reaches its maximum intensity, and the comet potentially undergoes its most dramatic transformations, Earth's astronomical community will be effectively blinded. The peak outgassing, possible fragmentation events, and maximum tail development could all occur during the weeks when ground-based telescopes cannot function effectively. This observational gap places extraordinary importance on spacecraft positioned throughout the solar system, particularly those orbiting Mars. The European Space Agency's Mars Express and Trace Gas Orbiter, along with NASA's Mars Reconnaissance Orbiter and MAVEN, suddenly find themselves in the role of humanity's primary eyes on one of the most significant astronomical events of the decade. The post-perihelion timeline offers both hope and realism about what observers can expect. Assuming 3I Atlas survives its solar encounter intact, Earth-based observations should resume in November or early December as solar elongation increases beyond practical limits. However, the comet will likely be fading rapidly by then, having exhausted much of its volatile content during the unobserved peak heating period. Magnitude predictions suggest that even at its brightest, 3IA Atlas will remain a telescopic object for Earth-based observers. Peak brightness estimates hover around magnitude 11 to 12, far too faint for naked eye visibility, but well within the range of amateur astronomical equipment. The lack of a spectacular naked eye show may disappoint casual observers, but it doesn't diminish the scientific value of this unprecedented interstellar encounter. The velocity profile reveals another crucial aspect of the 3I Atlas timeline. As the object approaches perihelion, its speed continues increasing under solar gravitational acceleration. However, immediately after closest approach, that same gravity begins decelerating the comet as it moves away from the sun's location. This velocity change affects the duration of peak heating and the time frame available for observation by Mars-based spacecraft. Looking beyond perihelion, the trajectory calculations show 3I Atlas continuing outward through the solar system, eventually approaching Jupiter in March 2020. While this encounter will occur at a much greater distance than the Mars flyby, it may provide additional opportunities for spacecraft observations as the comet begins its final exit from our solar system. The timeline creates a narrow window of opportunity that astronomy has never faced before. Unlike periodic comets that return regularly, allowing multiple opportunities for study, 3I Atlas offers a single chance to understand an object from another star system. The observational challenges, conjunction timing, and spacecraft opportunities must all align perfectly for humanity to extract maximum scientific value from this cosmic visitor. As we approach the critical October dates, the question isn't just what 3I Atlas will reveal about itself, but whether our observational capabilities will prove adequate to capture those revelations. The mathematics of orbital mechanics have set the schedule, and that schedule waits for no one. Part 5. Color shift. The green glow. The most visually striking change occurred in mid-September, when the entire comet began glowing with an eerie green light that signaled chemistry unlike anything previously observed in an interstellar visitor. In the middle of September 2025, 3I Atlas did something that sent ripples of excitement through the astronomical community. It turned green, not gradually, not subtly, but with a vivid emerald glow that transformed this interstellar visitor from a pale smudge into something that looked almost alive against the star-filled darkness. The color change wasn't immediately obvious to casual observers. 3I Atlas remains too faint for naked eye visibility, but sensitive cameras attached to telescopes around the world began capturing images that showed an unmistakable green tint surrounding the comet's nucleus. The transformation became particularly evident in photographs taken during the lunar eclipse on September 14th, when the moon's shadow provided darker skies that enhanced the contrast of the comet's newfound luminescence. The green glow tells a story written in the language of quantum mechanics and molecular chemistry. When certain molecules absorb ultraviolet light from the sun, their electrons jump to higher energy states. As these electrons fall back to their ground state, they emit light at specific wavelength that our eyes perceive as distinct colors. In the case of 3I Atlas, the green emission most likely originates from diatomic carbon, two carbon atoms bonded together, designated as C2 in chemical notation. Diatomic carbon behaves like a molecular neon sign in space. When energized by solar ultraviolet radiation, C2 molecules emit light at wavelengths around 516 nanometers, producing the characteristic green glow that has made 3I Atlas one of the most visually distinctive comets observed in recent years. This emission process, called fluorescence, transforms invisible solar energy into visible light that can travel across millions of kilometers to reach Earth-based telescopes. But here's where the story becomes puzzling. Early spectroscopic observations of 3I Atlas showed relatively little evidence for carbon-bearing compounds. The initial chemical analysis suggested a composition dominated by carbon dioxide and water vapor, with only trace amounts of the carbon-rich molecules typically responsible for green comet colors. This apparent contradiction between the observed green glow and the measured chemical composition has researchers scrambling to understand what's really happening in the comet's expanding atmosphere. One possibility involves phase transitions in the comet's outgassing behavior. As 3I Atlas moved closer to the Sun and crossed the 2 astronomical unit threshold in early September, increased solar heating may have begun sublimating previously inaccessible deposits of carbon-rich materials within the nucleus. These materials, locked away in the comet's interior during its long interstellar journey, might now be experiencing solar radiation for the first time in their existence. The timing of the green color change correlates suspiciously well with the period of rapid brightening observed in mid-September. This suggests that the same physical processes responsible for the unexpected brightness surge, possibly the catastrophic release of volatile materials from subsurface reservoirs, also triggered the chemical reactions producing the green emission. Alternative explanations for the color shift involve more complex chemistry than simple diatomic carbon fluorescence. Comets can contain dozens of different carbon-bearing molecules, each with its own emission characteristics. The apparent green glow might result from a blend of emissions from multiple species or from carbon-containing molecules unique to interstellar environments that don't exist in significant quantities among solar system comets. Instrument sensitivity and processing techniques also introduce uncertainty into color measurements. Different telescopes, using different filters and imaging systems, can produce subtly different color renditions of the same object. What appears distinctly green in one image might look more blue-green or yellow-green in another, depending on the specific wavelengths recorded and the methods used to combine them into color images. The evolution of the green glow provides additional clues about the underlying chemistry. Unlike the steady emission expected from simple molecular fluorescence, observations suggest that the green color varies in intensity and distribution within the coma. Some regions appear more intensely green than others, suggesting that carbon-bearing molecules aren't uniformly distributed throughout the expanding gas cloud. This non-uniform distribution could result from discrete outgassing events, where jets of material erupting from specific locations on the nucleus carry different chemical compositions. Alternatively, the variation might reflect chemical processing within the coma itself, as solar ultraviolet radiation breaks down complex organic molecules into simpler fragments that fluoresce at different wavelengths. The green emission also provides a diagnostic tool for understanding the physical conditions within the coma. The intensity of molecular fluorescence depends on the density of molecules, their temperature, and the intensity of solar ultraviolet radiation. By measuring how the green glow varies with distance from the nucleus and how it changes over time, researchers can map the three-dimensional structure of the carbon-bearing gas within 3I Atlas's atmosphere. Temperature measurements, derived from the green emission characteristics, suggest that the carbon-bearing molecules exist in a state of thermal equilibrium with the rest of the coma gases. This indicates efficient energy transfer between different molecular species, providing insights into collision rates and gas dynamics within the expanding atmosphere. The appearance of green coloration in 3I Atlas adds another data point to the growing catalogue of differences between interstellar visitors and native solar system objects. 1I Uwimomowa showed no clear signs of cometary activity, and thus no color changes. 2I Borisov displayed more conventional comet colors, dominated by blue and white scattered sunlight rather than molecular emission lines. 3I Atlas represents the first interstellar comet to develop the classic green coma that amateur astronomers associate with approaching periodic comets. However, the specific wavelengths and intensity of the green emission may differ subtly from those of familiar comets, potentially revealing chemical compositions unique to objects formed in other star systems. The timing of the color change creates additional observational urgency. As 3I Atlas approaches superior conjunction and becomes unobservable from Earth in early October, the green emission may continue evolving, or it could fade entirely. The peak intensity of molecular fluorescence often occurs near perihelion, when solar heating reaches its maximum, but this critical period will be largely hidden from Earth-based telescopes. Spectroscopic follow-up observations attempt to identify the specific molecules responsible for the green emission, but these measurements require large telescopes and favorable observing conditions that become increasingly difficult to achieve as the comet approaches the sun's glare. Each night of clear weather becomes precious, as astronomers race to characterize the emission before losing sight of their target. The green glow transformation represents more than just a visually striking development. It provides direct evidence that 3I Atlas is undergoing fundamental chemical changes as it encounters our sun's radiation. The molecules now fluorescing in the comet's coma have likely remained chemically inert for millions of years, preserved in frozen silence during the object's journey between star systems. Now, for the first time since its formation, 3I Atlas is literally lighting up. The solar energy activates chemical processes that had been dormant since the comet's birth around another star. The green glow marks the awakening of alien chemistry, the first stirrings of molecular activity in materials that formed under conditions possibly unlike anything in our solar system. But observing this awakening presents challenges that push the limits of ground-based astronomy, challenges that will soon force researchers to rely on mechanical eyes positioned throughout the solar system to continue monitoring our transformed interstellar visitor. Part 6. Challenges in observation. The universe has a cruel sense of timing when it comes to 3I Atlas, just as this interstellar visitor begins revealing its most intriguing secrets. The rapid brightening, the impossible coma, the alien green glow, the mechanics of orbital geometry conspire to snatch it away from Earth-based observers at the most critical moment of its journey. Professional telescopes, equipped with the most sophisticated instruments humanity can build, face the same fundamental limitation that frustrates backyard astronomers. You cannot observe what hides behind the sun's location. As 3I Atlas continues its approach toward perihelion, its position in Earth's sky moves inexorably closer to our star's overwhelming glare, creating observational challenges that no amount of technological advancement can overcome. The James Webb Space Telescope managed to capture spectroscopic observations of 3I Atlas on August 6, using its near-infrared spectrograph. These provided crucial chemical composition data during one of the few windows when the world's most advanced observatory could safely point toward the comet without risking solar damage. These observations represent some of the most detailed chemical analysis possible for an interstellar object, but they occurred before the dramatic changes of mid-September that transformed 3I Atlas from a merely unusual comet into an actively puzzling one. The Hubble Space Telescope contributed its own observations on July 21st, capturing high-resolution images that revealed the sunward-pointing plume structure and provided size constraints for the nucleus. However, since August, new high-resolution imagery from major space-based observatories has become sparse. The observatories that can provide the detailed analysis necessary to understand 3I Atlas's unusual behavior are the same ones most vulnerable to solar interference as the comet approaches conjunction. Ground-based observatories face their own cascade of complications. Different telescopes, using different filter systems and calibration procedures, produce brightness measurements that don't always agree with each other. This inconsistency isn't unusual in astronomy. Brightness measurement or photometry requires careful attention to atmospheric conditions, instrument calibration and standardization procedures that can vary between observatories. The Comet Observation Database attempts to reconcile these differences by collecting brightness reports from observers worldwide and plotting them against theoretical models. Throughout September, the COBS data clearly showed 3I Atlas trending brighter than predicted, with measured magnitudes consistently above the expected curve. But the scatter in individual measurements reflects the challenges faced by observers trying to track a rapidly changing object that defies their carefully constructed models. Amateur astronomers, often working with smaller telescopes and less sophisticated equipment, contribute valuable long-term monitoring data that professional observatories cannot always provide. However, their measurements face additional uncertainties from atmospheric turbulence, light pollution, and equipment limitations. The result is a patchwork of observations that collectively paint a picture of unusual behavior, while individually containing enough uncertainty to fuel debates about what's really happening. The Sky Live and other tracking websites compile these diverse observations into light curves that show brightness evolution over time. The sites that track 3I Atlas consistently show the same troubling trend, measured brightness points climbing above the predicted trajectory, particularly after mid-September. Yet the precise magnitude of this deviation remains uncertain, due to the inherent challenges in measuring faint, rapidly changing objects. Solar elongation, the angular separation between 3I Atlas and the Sun as seen from Earth, represents the fundamental constraint, limiting all observations. The elongation timeline creates a countdown that no human technology can extend. In early October, 3I Atlas drops below the 30 dictroubles threshold that marks the beginning of serious observational difficulties. By mid-October, elongation decreases to less than 20 dictray, effectively ending routine observations from Earth's surface. This period of invisibility extends through early November, encompassing the critical weeks when solar heating reaches its maximum intensity. The irony is palpable. We're trying to watch a cosmic firefly hovering next to a floodlight, using instruments designed to detect the faintest whispers of light from the most distant galaxies. Even adaptive optic systems that can compensate for atmospheric turbulence, and coronagraphs designed to block stellar light, cannot overcome the fundamental physics of scattered sunlight when the comet appears too close to the Sun's position in the sky. Space-based observatories theoretically possess advantages over ground-based telescopes in dealing with solar interference, but they face their own constraints. Instruments like Hubble and James Webb include protective systems that prevent them from pointing too close to the Sun, automatically shutting down observations when solar angles become dangerous. These safety systems, essential for preventing catastrophic damage to billion-dollar instruments, create observation gaps precisely when they would be most valuable. The timing of 3I Atlas's conjunction period couldn't be worse for understanding its peak activity. Theoretical models predict that maximum outgassing, possible fragmentation events, and the most dramatic tail development should all occur near perihelion in late October. These are exactly the phenomena that could reveal the most about 3I Atlas's composition, structure, and origins, and they will occur largely hidden from human observation. Data processing challenges compound the observational difficulties. Images of 3 Atlas must be carefully processed to separate the comet's signal from background stars, cosmic rays, and instrumental artifacts. As the object becomes fainter relative to sky brightness during its approach to conjunction, these processing steps become increasingly critical and increasingly prone to introducing errors or artifacts. Spectroscopic observations, essential for understanding the chemical composition of the comet's coma and tail, require even more specialized conditions than simple brightness measurements. The instruments needed to disperse comet light into its component wavelengths work best with bright targets observed under dark skies. As 3I Atlas fades into solar glare, opportunities for detailed spectroscopic analysis vanish just when chemical activity may be reaching its peak. The atmospheric limitations affect different wavelengths of light in different ways. Ultraviolet emissions, crucial for detecting many molecular species in comet comas, become particularly difficult to observe as elongation decreases, Because Earth's atmosphere scatters blue and ultraviolet light more efficiently than red wavelengths. This scattering effect, which gives our sky its blue color, creates additional challenges for studying the chemical processes occurring within 3I Atlas's expanding atmosphere. Coordination between observatories becomes essential. As observing conditions deteriorate, facilities at different latitudes and in different time zones must work together to maximize the limited observation windows available each night. Southern Hemisphere observatories may retain better viewing geometry slightly longer than their northern counterparts, creating opportunities for extended monitoring that require careful international coordination. The photometric scatter in brightness measurements reflects more than instrumental limitations. It may also indicate real variability in 3I Atlas's output. Comets can undergo rapid changes in brightness due to outgassing events, rotation effects, or structural changes in their nuclei. Distinguishing between measurement uncertainty and genuine comet variability becomes increasingly difficult as signal-to-noise ratios decrease during the approach to conjunction. Weather adds another layer of uncertainty to ground-based observations. Cloud cover, atmospheric turbulence, and seasonal weather patterns at major observatories can eliminate crucial observation opportunities that will not recur, unlike periodic comets that return predictably. 3I Atlas offers only a single passage through the inner solar system, making each clear night precious and irreplaceable. The challenge extends beyond individual observations to the broader question of how to interpret the data that does exist. The brightness trend showing 3I Atlas exceeding predicted values could indicate enhanced outgassing, structural changes, or simply systematic errors in the theoretical models used for comparison. Resolving these questions requires the kind of detailed long-term monitoring that becomes impossible as the comet disappears into solar glare. As Earth-based astronomy reaches its limits in observing 3I Atlas, the responsibility for continued monitoring shifts to mechanical eyes, positioned throughout the solar system. Spacecraft orbiting Mars, designed for entirely different missions, suddenly find themselves serving as humanity's primary observers of one of the most significant astronomical events of the decade. Part 7. The growing alarm among astronomers. Behind the measured language of scientific papers and the carefully qualified statements in astronomical bulletins, something approaching excitement and, yes, alarm ripples through the global community of comet researchers. 3I Atlas isn't behaving according to the scripts written by decades of cometary science, and astronomers are beginning to admit in the cautious way that scientists acknowledge uncertainty that they might be witnessing something unprecedented. The brightness trend documented by observers worldwide represents more than statistical noise or measurement error. Multiple independent tracking systems, from the Comet Observation Database to specialized amateur networks, show the same unsettling pattern. 3I Atlas consistently outshining the predictions derived from standard cometary models. The magnitude of this deviation, several brightness levels above expected values, falls well outside the margins typically attributed to observational uncertainty. Dr. Matthew Knight, a cometary scientist who has spent his career studying how these objects behave, recently noted in an interview that the rapid brightening event observed in mid-September challenges fundamental assumptions about volatile release mechanisms in comets. The speed of the change, he suggested, indicates processes operating on timescales much faster than the gradual heating models typically used to predict comet behavior. This scientific uncertainty breeds a particular type of excitement among researchers, the recognition that they might be observing phenomena that will require new theoretical frameworks to understand. Earth's skies reporting on 3I Atlas captures this tension, describing observations that continue to surprise researchers while acknowledging that much of what appears unusual might reflect the inherent unpredictability of objects formed in other star systems. The sunward-pointing plume structure generates its own category of scientific puzzlement. Anti-tail phenomena aren't unknown in cometary science, but the persistence and prominence of 3I Atlas's forward-directed jets push the boundaries of what existing models can easily explain. Researchers find themselves proposing increasingly exotic scenarios: unusual dust grain compositions, non-uniform nucleus rotation, exotic volatile mixtures to account for behavior that defies textbook explanations. What everyone in the field agrees on is that 3i Atlas is demonstrating enhanced activity levels compared to typical comets at similar distances from the Sun's position. The carbon dioxide-dominated coma, detected by HEFREX and extending to unprecedented distances, suggests outgassing rates that exceed standard predictions by significant margins. This isn't a subtle deviation from theory, it's a dramatic departure that demands explanation. Yet the scientific community also grapples with what researchers call outburst bias, the tendency for comets to undergo brief periods of enhanced activity that can create false impressions of sustained unusual behavior. Comets are notoriously prone to sudden brightness surges, followed by equally rapid returns to predicted levels. The question haunting 3i Atlas observations is whether the September brightening represents a genuine departure from normal behavior, or simply a temporary outburst that will fade as quickly as it appeared. This uncertainty becomes more troubling when considered against the backdrop of the approaching observational gap, the most critical period for understanding 3i Atlas's true nature, the weeks surrounding perihelion, when solar heating reaches maximum intensity, will occur largely hidden from Earth-based telescopes. If the comet undergoes its most dramatic transformations during this period, researchers may never understand what they witnessed in September. Dr. Carrie Holt, who studies interstellar objects at the European Southern Observatory, expressed the frustration felt by many researchers. The exact moment when 3i Atlas might reveal its most significant secrets coincides with the period when Earth-based astronomy becomes least capable of observing it. The timing represents what she termed a cosmic conspiracy against scientific understanding. Yet, its interstellar origin and unusual behavior generate excitement among those who understand its significance. Educational institutions worldwide are incorporating 3i Atlas observations into classroom activities, using the comet as a real-time example of scientific discovery and progress. Students can follow the observational campaigns, analyze publicly available data, and witness how scientific understanding evolves as new evidence emerges. The commercial space industry shows increasing interest in small body studies, recognizing both scientific value and potential economic opportunities in asteroid and comet characterization. While 3i Atlas presents no mining or resource extraction opportunities due to its hyperbolic trajectory, the techniques developed for studying it contribute to broader capabilities for characterizing small bodies that might prove commercially valuable. As we approach the critical October dates, 3i Atlas has already succeeded in demonstrating that interstellar visitors will consistently challenge our assumptions about what's possible in the universe beyond our solar system. Whether the comet's future behavior confirms current theories or introduces entirely new puzzles, it has established a new standard for the unexpected in astronomical phenomena. The final hook line that will define 3i Atlas's legacy depends on what observations reveal during the crucial weeks ahead. 3i Atlas is beginning to reveal what it truly is: a chemical time capsule from a Morton-sick, another star, a physics laboratory operating under conditions never before observed, or perhaps something even more extraordinary that will force us to rewrite our understanding of what wanders between the stars. In the next few weeks, it will either flare into unprecedented brightness, fragment into a cascade of interstellar debris, or slip quietly past our sun, carrying its secrets back into the cosmic dark. And whatever happens could fundamentally change how we think about visitors from other suns. The call to action for anyone capable of following this cosmic detective story is clear. Watch for mission image releases from ISS's Mars Express and Trace Gas Orbiter, NASA's Mars Reconnaissance Orbiter, and MAVEN, then await the post-perihelion updates from Hubble Space Telescope and James Webb Space Telescope that might finally reveal what 3i Atlas truly represents. The universe has sent us a messenger from another star, and we're about to learn what message it carries.